When we think of Antarctica now, we picture a continent locked under ice. White, wind-cut, nearly silent. But deep in Earth's history, this land carried a very different expression. Long before it became an isolated mass at the South Pole, Antarctica formed part of Gondwana, the vast southern supercontinent that held together for tens of millions of years, before beginning to fracture during the Jurassic and continuing to separate through the Cretaceous. From that slow tectonic breakup, Antarctica drifted into a geographic position unlike any other, far enough south to become distinct, not yet cold enough to disappear beneath permanent ice. What emerged was not the Antarctica of glaciers and exposed rock, but a continent of forests, wetlands, and dense plant communities. The ground would have felt dark with moisture, the air cool, humid, and heavy with organic decay. Water moved through floodplains and low forest floors. Conifers and understory plants filled the landscape with structure. On the surface, it looked stable, green, productive, alive. But the governing pressure was not temperature alone. It was light, not a daily cycle, but seasons stretched to extremes. Long brightness, then prolonged darkness. Within that altered rhythm, life did not merely endure. It had to be redesigned. Climate and the paradox of light cycles. Say the word Antarctica to almost anyone, and the image is immediate. White, silent, biologically vacant. A continent defined by absence. That assumption is geologically incorrect. During the Cretaceous period, the landmass now locked under kilometers of ice sat near the southern polar edge, and it was forested. The evidence is preserved in the James Ross Basin, where sedimentary layers stack to a depth of roughly 6,000 meters, taller than 10 CN towers, placed end to end. That is a rock record of extraordinary resolution, and it tells a story the modern landscape works hard to conceal. But warmth alone doesn't explain what was living here. For that, we go deeper into the rock itself. The evidence arrives in two forms. First, marine shells, ammonites, belemnites, nautiloids, bivalves, whose oxygen isotope ratios function as ancient thermometers, preserving the temperature of surrounding seawater with considerable fidelity. Second, fossilized wood, still carrying clearly defined annual growth rings, each one recording a seasonal rhythm, like entries in a slow, patient diary. Laid side by side, these datasets don't merely suggest a climate, they reconstruct one, and the figures are not what you'd expect. At James Ross Island, average annual temperatures reached roughly 11.7 degrees Celsius, comparable to the year-round average of Vancouver. Further south, near 82 degrees south latitude, fossil forest soils record annual averages of 12 to 13 degrees Celsius. Temperatures that today characterize the rainforest coasts of southern Chile, or Hobart, Tasmania. The warmest months averaged around 18.4 degrees Celsius, a mild Sydney autumn afternoon. Freshwater systems, rivers, wetlands, shallow floodplains, reached up to 20 degrees Celsius. Annual precipitation is modeled at approximately 1,120 millimeters. Auckland levels, sufficient to sustain dense, old-growth temperate rainforest, not dry woodland, not tundra. This degree of sustained warmth at this latitude required something structural happening in the atmosphere itself. Climate simulations can only reproduce these conditions when atmospheric CO2 is set between 1,120 and 1,680 parts per million. 4 to 6 times the pre-industrial baseline of 280 parts per million. The air filling this forest held the CO2 concentration you would find inside a poorly ventilated greenhouse on a warm afternoon. except this was the entire planet's atmosphere. Every breath, every current, every leaf surface, saturated by it. That atmosphere sustained something on the ground that no modern visitor to Antarctica could reasonably prepare for. Stand inside this forest. The canopy above you is almost entirely coniferous. Fossil wood records from the Santa Marta Formation show conifers accounting for roughly 84% of sampled specimens, 5 out of every 6 trunks drawn from the same gymnosperm lineage, Araucariaceae, Podocarpaceae, families with living descendants today along the coasts of New Zealand and southern South America. Beneath that canopy, ferns, ginkgo, and early flowering plants. A dense, stratified understory feeding organic matter into waterlogged soils. Remove the geographic context, disregard the latitude entirely. This landscape, structurally, ecologically, would be indistinguishable from a modern temperate rainforest. It was a stratified, functioning world, built on conditions so removed from anything Antarctica represents today that the geological record remains the only credible witness. Plant life. Survival strategies in the dark. Yet a forest standing in place is only half the story. What this landscape demanded, from every organism rooted within it, was not merely the capacity to grow, but the capacity to stop. Precisely, repeatedly. On a geological schedule governed not by temperature, but by light. At these latitudes, winter did not simply bring cold, it erased the sun entirely. For about 5 months, polar night descended, total, uninterrupted darkness across a landscape that, by every other measure, remained biologically productive. Summer reversed the equation with equal severity, nearly continuous daylight, 24 hours cycling without true night. The photosynthetic engine these forests depended on was not a steady current, it was a pulse. Fossil wood from the James Ross Basin and Alexander Island makes this visible in cross-section. Growth rings in Antarctic specimens follow a consistent and telling pattern. Wide early wood laid down rapidly during favorable light conditions, transitioning sharply into narrow, compressed late wood, sometimes terminating so abruptly that the boundary reads less like a gradual seasonal shift and more like a biological circuit breaker tripping. Growth did not taper. It stopped. This translates to a two-phase existence. During the sunlit season, these plants operated at high productive capacity, accumulating biomass, extending root systems, generating the carbohydrate reserves that would carry them through what followed. During polar night, metabolic activity contracted to its functional minimum. Not death, not dormancy in the colloquial sense. A precise, regulated reduction. The organism spending as little energy as the chemistry of survival would permit. 2 distinct strategies emerged in response to this constraint. Deciduous species shed their leaves at the onset of darkness, eliminating the surface area responsible for both photosynthesis and water loss simultaneously. The logic is straightforward. A structure that cannot produce energy becomes a liability the moment production ceases. Evergreen conifers followed a different calculation. Their needle-like or scale-shaped leaves, narrow, low in surface area, sheathed in a thick cutin layer, remained attached year-round. The cost of retention was offset by the reduced metabolic overhead these leaf forms demanded. Even so, retention did not mean activity. Through the dark season, these trees remained completely dormant. Both strategies converged on the same outcome, a forest that functioned less like a continuous system and more like a carefully managed energy reserve. That reserve sustained more than wood and leaf tissue. Something was moving through it. Terrestrial animals. Adaptation to a polar energy system. Many of the animals inhabiting this forest had no option of simply migrating to escape or entering deep torpor to wait out the dark. Survival here was a problem of timing. The productive season was finite, a concentrated window of biological abundance, bracketed on both sides by scarcity. Fossil evidence from the Santa Marta Formation and Snow Hill Island Formation reveals a terrestrial community shaped less by competition for space and more by the capacity to synchronize with an interrupted energy calendar. Species diversity was not the defining characteristic of this ecosystem. Ecological precision was. What emerged was a community structured around discrete roles, each occupying a position within a food web calibrated to seasonal surplus and seasonal deficit. Not the most species-rich fauna on the late Cretaceous polar landmass, the most functionally organized. At the base of that structure stood the animals responsible for converting plant matter into accessible energy, and they left their own record in the rock. Herbivores, engineers of the polar forest. The forest floor of Cretaceous Antarctica was not an open landscape. It was a dense, stratified system of ferns, low shrubs, and decomposing organic matter. And moving through it, at roughly 4 meters in length, was Antarctopelta oliveroi, the first dinosaur ever discovered on this continent. At the scale of a station wagon, low-slung, heavily armored, this ankylosaur did not pursue food. It processed it, methodically working through ground-level vegetation with a body plan engineered for sustained, low-energy foraging. Not speed, not range, endurance. In a seasonal ecosystem, that distinction carried considerable ecological weight. But not every herbivore in this forest resolved the problem of scarcity through mass and armor. Some resolved it through the opposite. Trinosaura santamartiensis measured approximately 1.5 meters in length, roughly the span of a standard office desk. Lightweight, bipedal. Equipped with a beak and dentition calibrated precisely for soft vegetation. Where Antarctopelta worked through whatever the understory offered, Trinosaura was selective, built to exploit brief pulses of nutrient-dense young growth during the light season, then seek refuge to conserve energy. Reduced body mass meant reduced energy expenditure through the dark months. Smallness here was a derived ecological solution. Between the armored and the agile, a third animal occupied the middle ground. And its presence indicated something beyond diet. Morosaurus antarcticus, another ornithopod from James Ross Island, carried moderate body mass and correspondingly measured metabolic demands. Its ecological function was analogous to a white-tailed deer in a temperate forest. Broad dietary range, viable caloric overhead, capable of exploiting varied vegetation without accumulating unsustainable energy debt across the dark season. Its biogeographic significance was equally notable. Its closest known relatives were South American. Morosaurus was skeletal confirmation that Antarctica, even as Gondwana continued to fragment, retained active faunal corridors to the north. Yet these three species together do not complete the assemblage. An incomplete section of a tail vertebra places Titanosauria, the large-bodied sauropods, within this ecosystem. One element, sufficient to confirm presence, insufficient to establish ecological centrality. In a system governed by concentrated seasonal energy pulses, sustaining an animal with the caloric requirements of a large sauropod through prolonged polar darkness would have been metabolically untenable. The fossil record's restraint on this group is, in itself, a data point. Where herbivores occupied structured, precisely calibrated ecological positions, something else was tracking that structure and calibrating accordingly. Predators, pressure in a dark forest. That calibration had a name. Imperabator antarcticus is known from hind limb material recovered from the Cape Lamb. Member of the Snow Hill Island Formation, tibia, ankle bones, metatarsals, toe elements, dating to the early Maastrichtian. Fragmentary, but diagnostic. The preserved bones place it as a Paravian measuring over 3 meters in length and standing close to 2 meters tall. Recent phylogenetic analysis suggests it is a basal Paravian, completely distinct from the northern dromaeosaurid lineages more familiar to most. The foot architecture is instructive. No evidence exists of the extreme sickle claw morphology associated with conventional depictions of this group. What the bones indicate instead is a limb configuration suited to agile, directional movement through structurally complex vegetation. A forest predator, not an open-country pursuit hunter. In a closed canopy polar rainforest, that distinction was functionally decisive. The seasonal rhythm governed its behavior as directly as it governed everything else in this system. During the light season, herbivore activity intensified. Prey distribution widened. Hunting opportunities across the forest floor and understory became viable and relatively frequent. As polar night advanced and prey withdrew into physiologically conservative states, the energetic calculus of each predatory attempt shifted substantially. A failed hunt in darkness carried a metabolic cost that a failed hunt in midsummer did not. Predation here was not a continuous pressure. It was periodic, concentrated, deliberate, and contingent on the same light cycle that regulated every other organism within this system. This forest functioned as a complete, internally coherent ecological unit. But the forest was not the whole of Antarctica's Cretaceous world. Wetlands and coastal zones, where Antarctica's ecosystem reveals its true rhythm. The forest had its rules. The coast had different ones entirely. Step away from the conifer canopy and move toward the continent's edge, where freshwater draining from the interior met tidal saltwater pushing inland. The result was not a clean boundary. It was a zone of continuous chemical negotiation. Estuaries, brackish wetlands, and shallow marine margins, where salinity shifted with each tide, and water levels responded to every seasonal pulse from the land above. This was not a stable habitat. It was a system defined by perpetual flux. And the organisms that established themselves here were precisely those whose physiology accommodated that variability, rather than requiring refuge from it. The sedimentary record of the Marambio group documents a productive, shallow marine system extending along Antarctica's Late Cretaceous coastline. Moving through it continuously from the Coniacian to the Late Maastrichtian were the elasmosaurids. Their locomotion was not configured around speed. 4 large, paddle-like limbs operated as independent propulsion units, precision instruments for 3-dimensional spatial positioning rather than sustained velocity. In a coastal environment structured by kelp margins, estuarine shallows, and variable water clarity, the capacity to hold position and redirect precisely outperformed the ability to accelerate. These animals navigated their environment with a degree of hydrodynamic control that raw pursuit predators could not replicate. One aristonectine specimen from the Lopez de Bertodano Formation carried an estimated mass of 11 tons, the combined weight of 2 fully loaded cement mixer trucks, moving under its own locomotor authority through Antarctic coastal waters. Its fossil rests less than 2.3 meters below the KPG boundary, a stratigraphic interval no greater than the height of a standard interior door frame, separating its existence from one of the most consequential extinction events in Earth's history. Antarctic waters, at that margin, remained productive enough to sustain it. But positional control of a water column and apex dominance within it are not equivalent claims. A second predator operated on fundamentally different anatomical logic. Chicxulub hervae is documented from the upper beds of the Lopez de Bertodano Formation. Its skull measures an estimated 1.2 meters, longer than a standard acoustic guitar, and enclosing jaw mechanics engineered for prey selection, well beyond what most contemporary predators would have attempted. Elongated body, robust, interlocking dentition, a mosasaur whose osteological profile leaves its ecological designation unambiguous. Finding oneself within its operational range would have represented a terminal navigational error. Its stratigraphic persistence across Antarctic deposits confirms that these coastal seas sustained sufficient vertebrate prey biomass to support a predator at this metabolic tier, at minimum across productive seasons, and possibly through the full annual cycle. Yet the predatory structure of this coastline extended beyond two principal actors. A third tier was operating below the surface, phylogenetically older, physiologically more versatile, and considerably more resistant to ecological displacement. Shark teeth recovered from Maastrichtian age deposits identify Cretalamna and Notodonodon as concurrent occupants of this system, alongside the large marine reptiles. These were not marginal presences. Their ecological value resided in what separated them from the reptilian predators above them in the water column: tolerance for salinity gradients, dietary breadth across prey categories, and access to the shallowest coastal margins, zones where an 11-ton elasmosaurid simply could not operate with efficiency. The outcome was not competitive exclusion. It was resource partitioning, discrete predatory strategies distributed across overlapping but functionally distinct ecological registers within a shared food web. Each tier exploiting the spatial and dietary dimensions the others left accessible. And then, operating at the outermost margin of this entire system, lighter, more derived, and belonging to a lineage no one in this ecosystem would have recognized as ascendant, was Vegavis iai. Recovered from the Cape Lamb member of the Snow Hill Island Formation on Vega Island, Vegavis was not a reptile. It was a bird, an early representative of the crown group lineage that would eventually produce modern waterfowl. Its skeletal morphology indicates functional diving capacity, a body plan oriented toward subaqueous prey acquisition in the manner of derived aquatic birds, not the generalized avian forms typical of the broader Mesozoic record. Its presence within a coastal system still dominated by plesiosaurs and mosasaurs was not anomalous. It was consequential. It confirmed that neornithine bird lineages had already negotiated a stable functional position within a late Cretaceous marine ecosystem, present, operating, and ecologically established well before the architectural collapse of the world around them. What this coastline recorded was not simply a roster of species. It was a document of transition, ancient lineages at full ecological expression, and newer ones quietly taking positions they would inherit entirely. Something was coming that neither group had any means of anticipating. Collapse. The end of a flourishing era. It arrived without precedent. The fossil record offered no warning. For millions of years, this ecosystem had operated under a demanding but internally consistent logic. Light accumulated, darkness conserved, and every organism from the forest floor to the coastal shallows calibrated its biology to that repeating interval. The system was not fragile, it was precisely tuned. That precision became its liability. Around 66 million years ago, an asteroid estimated between 10 and 15 kilometers in diameter, wide enough to span a major metropolitan area from edge to edge, struck what is now the Yucatan Peninsula. The Chicxulub impact injected silicate dust, sulfate aerosols, and combustion soot into the upper atmosphere, at a scale that fundamentally reconfigured the planet's energy budget. Solar radiation reaching the surface collapsed. Temperatures dropped across latitudes. Recent global climate modeling indicates the resulting darkness persisted not for weeks, but for up to 2 years, with sub-freezing conditions across many regions extending for over a decade. For lower latitude ecosystems, this was severe. For Antarctica, it was structurally precise destruction. Polar plant life had already evolved to endure prolonged darkness. Deciduous species shed leaves and down-regulated metabolic activity. Evergreen conifers compressed their physiology to functional minimums. These were well-established, demonstrably effective survival mechanisms, but they operated on one non-negotiable assumption: that light would return on schedule. When atmospheric particulates extended darkness well beyond the predictable polar night, that assumption failed. Photosynthesis could not resume within the interval these organisms were physiologically configured to wait. Carbohydrate reserves, accumulated during the preceding light season, were exhausted against a darkness interval with no biological precedent. The plant layer began to fail. What followed was sequential, and, in geological terms, rapid. Herbivores dependent on seasonal vegetation lost their primary energy source. Antarctic ornithopods and chylosaurs, the broader assemblage of ground-level consumers, all were operating within a food web already structured around constrained caloric margins. When the plant base contracted, that margin was eliminated entirely. Predators followed. A system that had sustained apex predators through periodic, calculated hunting could not sustain them through an indefinite collapse of prey availability. The food web did not erode gradually, it unraveled from the bottom. Large-bodied species carrying high metabolic requirements and deep structural dependence on terrestrial food chains were the least positioned to absorb this disruption. Non-avian dinosaurs, in Antarctica as across the globe, did not survive the boundary. But not every lineage the Cretaceous had built went with them. Some had already established positions at the margins, smaller, more generalist, less committed to the food chains now dissolving beneath them. And one of them, at least, had been present on this coastline all along. Quietly and with considerable foresight, the fossil record only reveals in retrospect. Not every ending leaves a clear scar on the surface. Some systems function for millions of years with remarkable precision. Light against darkness, abundance against scarcity. Then they fail with geological suddenness, when an external force exceeds every limit life was built to tolerate. What remains is not silence, it is storage. Today, Antarctica lies beneath kilometers of white ice and appears almost vacant. Yet below that stillness, deep sedimentary layers preserve a buried record of another world. In those layers are the traces of wet forests rising under seasonal light, heavy ornithischian herbivores moving through dense ground vegetation, marine predators patrolling coastal water. None of it is truly gone. It has simply been sealed in place, like a biological archive closed but not erased. The ice above is quiet enough to seem final, but the rock below still holds leaf impressions, bones, and chemical signals from vanished seasons. That collapse leaves behind a durable rule. Size and ecological dominance do not guarantee long-term survival. When the primary productivity of a system fails, the organisms most dependent on steady intake are often the first to become untenable. Smaller forms, with lower caloric demands and greater ecological flexibility, proved to possess the more prudent evolutionary arrangement. When the dust settled, the world did not resume its previous pattern. A vacancy opened, light returned, and life began again, not by restoring the old system, but by replacing it.